This podcast is brought to you by LMU Munich.
So we continue, and here the second part on black hole paradoxes.
Thank you, Ilke. Good morning. So actually I made a little change in the order. So we will start lecture 2 by asking the question, what if the evolution is unitary? You recall from the previous lecture that we followed Hawking's calculation, couldn't find any problem with it, and the conclusion was that unitarity is not preserved. Unitarity is violated. Now, to many, this is an unacceptable conclusion. And despite the fact that we couldn't find some concrete problem with the calculation, we know from many, many other situations that unitarity is preserved, quantum mechanics is correct. And so we are trying to assume that somehow there was some problem with the Hawking calculation, and we try to see how to implement the idea that unitarity is preserved and see what happens, see what the consequences are. Okay, and what I would like to discuss in this context is the page model. This is a few papers by Don Page from '93, which implements in the simplest way the idea that unitarity is preserved, and I will try to explain it. Now, after a short description of what the page model is, we will find out that we need to understand the nature of the would-be of the outgoing radiation, or the way that we model it, and we need to understand how to determine whether eventually the radiation purifies and unitarity is preserved. Okay, so we will have to make a digression, a technical digression, to explain measures of purity. And it turns out that the tool that you're probably most familiar with, which is the von Neumann entropy, is most familiar but not most useful. So we will have to get to know more useful tools for these measures of purity. And after we find out what these tools are, we will be able to draw the page curve very easily. The page curve was derived by Page in these papers in '93 by doing a simulation, a computer simulation. And here what I will show a very simple analytic calculation that reproduces that. Okay, and I think, I'm not sure if we will get to this page curve, and then the continuations will be about the consequences of the page curve, the firewall paradox, and similar things. But this probably will be in the next lecture. So, what is the page model? this is the page model. So basically what he's saying is the following. We have a black hole that is emitting radiation. We saw that in the previous lecture. Let's divide our world into the black hole, and it doesn't have to be separated by the horizon. You can do a larger region around the black hole, let's say, of at 10 Schwarzschild radii or something like that, so that you encompass the black hole in the whatever goes nearby, and then the out, which is the emitted radiation, emitted Hawking radiation. Okay. Now, what he is saying then, that since we are considering the possibility that unitarity is preserved, we say that there is some pure state that describes this system. It's in a quantum pure state. It doesn't have to be, in this case, it doesn't have to be in a pure state. We can discuss these issues also in cases where the initial state is mixed, but it's much easier to do it when the state is pure. Okay? So we start like that. And then there is some unitary evolution operator, U, that acts on this state. And after a while, in a schematic way, well, this was, yeah, in a schematic way, we can write it as a, like so. So it evolves into a very complicated state in some basis that we choose for this system. Okay, this is the standard thing that happens when you have unitary evolution. So we started with some state, and then it becomes some complicated state. Here there is a sum over. Okay? Now, what this means in this case is that if we look at the density matrix that describes this state, in some basis, rho has a single entry, right? So it's a pure state. We will discuss density matrices. There will be also problems about that, but this is the case. I can choose the direction of the psi to be one of my basis states, and then the rest, the other coefficients, vanish. Okay, so but in this basis that we are using to describe the system, the state looks extremely complicated. And there is some complicated unitary transformation, right? That makes rho diagonal. The idea that Page had was to treat this matrix statistically. So he said, we don't know what this matrix is. The evolution that propagates, that evolves the wave function is very complicated. Let's try to treat this unitary matrix as a random unitary matrix and discuss its statistical properties. Okay? And then find out what the properties of this density matrix in the complicated basis is statistically. And this should be enough to learn important things about the evolution, whether the radiation purifies, where it doesn't, and so on. So this is the basic idea. And in this case, there's one more ingredient that Page included in his model, and this is the fact that this division between the in and the out can move. And why is that? Maybe somebody has an idea. Why is it that we need to allow this division to change? Okay. No. So what is how are these in and out spaces characterized? The simplest characterization, which actually Page used, is the size of the size of the Hilbert space. Okay. Now, when the black hole evaporates, it is becoming smaller. Its entropy is decreasing. So we use that as a measure of the size of the Hilbert space. E to the entropy is the size of the Hilbert space. So, and there's more particles are radiated. So the Hilbert space of the out radiation is growing. So initially, we had everything was essentially a black hole, and then the black hole radiates. There's more and more radiation. So this division moves. The size of the Hilbert space of the black hole becomes smaller, and the size of the Hilbert space of the radiation becomes bigger. Is this clear? Good. Okay, and then what Page really wants to compute is the so-called reduced Again, the idea is that we have access to only to the outgoing radiation. Okay? Since we have access only to the outgoing radiation, we have to trace by the rules, the standard rules of quantum mechanics tell us that all quantities that we measure, this is in fact something that I will explain in this next sections about the measures of purity. All quantities are determined by the reduced density matrix of the radiation. So what we really want to do is study statistical properties of the reduced density matrix. Okay, is this clear so far? Questions? Very good. Now, one other point that I wanted to make, and I already made it, but I want to perhaps clarify it, is that these type of calculations do not involve a specific dynamic, specific Hamiltonian. You remember when we did the Hawking calculations, we had some trajectory of light rays, we were calculating the frequencies, etc., etc. Here, these type of ingredients will not be present. We will only use essentially ideas about density matrices and etc., or properties of density matrices. And so using this type of concept, we are inevitably led to quantum information ideas and methods. Okay? So we made a switch from a very concrete dynamical analysis of the radiating shell to a more abstract description of the state of the black hole and the radiation. And because many of us, including myself until quite recently, are not very familiar with these type of tools, what I would like to do now is explain in quite some detail and also give problems so that you can train in learning these concepts about measures of purity. We have to decide eventually if the outgoing radiation is becoming closer to a pure state or not, right? Because this is what will tell us whether the evaporation is unitary. If the outgoing radiation eventually is still thermal or close to thermal, as we were finding before, then we cannot answer the question, what if the evolution is unitary, because it is not. So we have to find somehow some criteria to check the nature of the outgoing radiation. So, and for that, we need to go to the next step, and that is this measures of purity, and I call it here brief reminder, although to some of you it might not be a reminder, about density matrices, reduced density matrices, and what else? Entropy, entanglement, purity, and information. So we have to learn how to learn this concept and learn how to use them. This is what I will do now. So what we will consider is a so-called bipartite Hilbert space. So it's a Hilbert space that is a product of two, like the situation that we have here, the in and the out. This doesn't mean that there are no interactions between these Hilbert spaces, but just the structure of the state space is of this type. And so in general, a general state in this space, I can write as a matrix the wave function of this form, just like we had with the in and out spaces. Now, by rotating independently the two sets of states, we can prove the Schmidt decomposition theorem. I will not do it. You can look at Wikipedia is good enough for the explanation of this. And we find that we can bring the state into a much simpler form, like so. Right? So we can turn it into the sum into a single term. The density matrix rho is defined as this operator. In fact, it is these density matrices are a much better way to understand quantum mechanics than wave functions. They make everything much clearer. These are matrices, matrix elements, algebraic operations, and things become clear. Now, we can now define the reduced density matrix. So the reduced density matrix, let's say rho 1, is defined as trace 2 of rho. This, what does it mean here? It means that I have to sum k and to take the trace. Like so, of the state in space 2. This is what it means to take the trace. Okay. Now, this I can explicitly do, right? Because this is sum over k, gamma k, and then I take this this matrix in this form, delta ij, ai, alpha I tilde 1, beta I tilde 2, and then then I have to multiply it by the kit, right? Delta RS, AR star, alpha R tilde 1, beta tilde S2, and then gamma K2. And then I can continue here, and I get sum over K. You see here, from that I get delta Ki, and from that I get delta Rk. So I get delta Ki, delta Ij, Ai, alpha I tilde, delta Rs, delta Sk, alpha R tilde. Yes, thank you. So you see the final result here now is that rho 1 is equal to AK star alpha K tilde 1 alpha K tilde 1. So now this is called the reduced density matrix. I could have done this a similar reduced density matrix for space 2. Now look at this density matrix and try to see what happens. First of all, now we have an operator that acts only on space 1, right? Space 2 has gone. Second, we started with a pure state, right? Because it had a wave function, and so it's pure. It could be an entangled state. It could have terms, a number of terms in a basis, but it was a pure state. Now, what about this one? No longer pure, right? Because it has more than one element on the diagonal. So when, in this case, this is a familiar phenomenon from quantum mechanics, when we trace out, we start from some pure state and we trace out some part of the state, in general, we will find a state that is not pure. Okay. Now, so this is the reduced density matrix, and now we find a very good use to the reduced density matrix. Suppose that we have an operator that acts only in Hilbert space 1. Okay? We can define operators like that. The claim is, and you will have a problem that shows that in the that if I want to calculate expectation values of operators, restricted operators, I have an operator that looks only, is sensitive only to one Hilbert space. As in the case that we're thinking about the radiation is going out and we are only making measurements on the outgoing radiation. So we are not making measurements in space 2, just space 1. In this case, the matrix element in a pure state is really a statistical average over a density matrix that is not pure. Okay? And this is, there is nothing wrong with this type of calculation. This is the standard rules of quantum mechanics tell us that this is the case. Okay, very good. So now we have to, the next step is to try and understand properties of the reduced density matrices to see, to track their purity or how close they are to a pure state, etc., etc. Okay? Very good. Questions so far? No? Everything is clear. So now let's try to get acquainted with measures of purity. So here, essentially, we're interested in a very simple question. We have a density matrix, and we would like to know how many non-vanishing eigenvalues this density matrix has. If it has one, it's pure. If it has many, it's not pure. And then essentially the number of non-vanishing eigenvalues is telling us how pure the matrix is. This is really a very simple concept. Now, unfortunately, the most familiar measure of purity is the von Neumann entropy. And somehow it hides the simplicity of this question. That I'm sure you're all familiar with, which is essentially some I, pi. Right? The pi's are the probabilities, and because they are less than 1, minus log is a positive quantity. Now, this, as you can see, is essentially telling you that if the eigenvalue vanishes, you don't get a contribution to this sum, and if it is non-vanishing, you get a contribution to the sum. Of course, you can think about the states that are very complicated, where you have, if you are a mathematician and want to invent complicated matrices with eigenvalues that jump around and so on, you can invent that. But since we're physicists, we're not interested in these type of inventions. And for most states, the eigenvalues are either large or small. And so this is really a measure of how many non-vanishing eigenvalues we have. It has other properties, but okay, so let me just remind you that in this case, if rho is pure, then S is 0, because pure rho means that, let's say, P1 equals 1, and the others vanish. So in this case, the contribution of the vanishing eigenvalue vanishes, and the log kills the eigenvalue that is 1, so you get 0. So a pure matrix has zero entropy. This is something that you probably know. And if rho is maximally mixed, or thermal, I don't distinguish between these two options, so that in this case pi equals 1 over n, because we usually like to keep trace rho, n is the number of eigenvalues, and for trace rho equals to 1, we need all the eigenvalues to be 1 over n. And then this sum gives me, right, sum I equals 1 to n, 1 over n log n, which is ln n. Now, the problem, so this is a very nice quantity. We all learned about it. We know it from statistical mechanics, etc., etc. The problem is that it's extremely impractical. Why? Because of the log. To compute, suppose that we have some matrix and we want to compute its log. Then the only way to do that is to diagonalize it and compute it with in the basis where it's diagonal, and then I know how to do it. But to diagonalize a matrix is in general a problem, in particular if we are interested in big, complicated matrices. So it is a nice conceptual quantity, but very impractical. Yes?
Sorry, but if it's big enough, shouldn't the eigenvalues be Gaussianly reparted?
That depends on the properties. If you have a pure state, and the eigenvalues are not distributed in a Gaussian way, right? So we are not thinking about statistics yet. But so you're right that when we will go to random matrices, then the eigenvalues will have a statistical distribution that obeys the central limit theorem. This is true. But here we would like to, in this case, look also on states that are not necessarily random. And in that case, it's also, you will see that it's still more complicated because of the log. So let's say that the eigenvalues are distributed Gaussianly, then their log will not be distributed Gaussianly. It will be more complicated, right? And the whole point is that we don't have to work with this quantity. There are better estimates of purity that do not force us to think about the eigenvalues. Okay? And this is what I want to explain. First time that I touched the correct button. Okay, so this was the most familiar, and now let's go to the most useful. It turns out that the most useful estimates simply involves trace row square. So to calculate trace row square, we don't need to know the eigenvalues. We just multiply, right? We multiply the matrix by itself, and then we sum the diagonal. Now, this is sum pi square, right? So you see, in this case, it's also counting how many non-vanishing eigenvalues there are. Because if the eigenvalue is large, it is counted. If it is small, it is not counted. And in the middle, we have some kind of a sort of effective number of eigenvalues. And you will get a problem to evaluate this. You will see it's a very good measure of how many non-vanishing values are. And the advantage is that it's very easy to calculate. And in fact, so the first such estimate is the purity. It's trace row square divided by trace row square. So if rho is normalized, then P is simply trace row square. Now let's see, in this case, what is the value in the two extreme cases. So if rho is pure, what is the purity? You can do this calculation in your head. 1. Good. You see, right? Because there's one eigenvalue of size 1. The rest are 0, so you get 1. And if rho is maximally mixed, one over n. So that's the purity, and now we can define the participation ratio. So in this case, I denote it by PR. I don't know what. This is sometimes the purity is called the inverse participation ratio because the participation ratio is defined like 1 over the purity. And in this case, for our two extreme cases, if rho is pure, what is the participation ratio? 1 over 1, right? So, and the maximally mixed, so you see in this case, it actually counts the number of non-vanishing eigenvalues. And in fact, this is the most direct measure of the number of non-vanishing eigenvalues. And I think you will get the problem showing that, maybe let me write the problem now. I still need a few other definitions to do the problem. So you see, calculating the participation ratio for an arbitrary matrix, it's much easier than calculating the von Neumann entropy. So we should get acquainted and get used to using it. Now, another quantity that is related to this estimate is called the Ramy entropy. I understand that now it became very popular, and you can understand why. Actually, it's the second Ramy entropy of order 2. And this H2 is the log of the participation ratio, or it's, in this case, is minus the log of P. So it's the log of 1 over trace row square. if rho is normalized. And you see this is equal to minus log of some px squared. So now the log has reappeared, but it has reappeared as the log of the sum of the eigenvalues. I don't need to take the log, diagonalize and take the log of the eigenvalues. I can take the log of the sum of the eigenvalues. And it's a much easier quantity to evaluate. And again, we can, for a pure rho, H2 is equal to zero. So, and for maximally mixed, log n, right? Because so you see it gives the same answers as the von Neumann entropy. In other cases, it gives slightly different answers, but you see that it has the same content, same conceptual content, and it's much easier to calculate. And it turns out, actually, if we are interested in field theories, in quantum field theories and so on, I'm not sure to what details we will see it, but for weakly coupled field theories, this quantity is essentially equivalent to the von Neumann entropy. So it's much easier to use.
Is that the reason why you call it an entropy?
Remy called it, the person who invented it was Remy. I didn't invent it, and he called it an entropy because it's a measure. An entropy is really a measure of how many non-vanishing eigenvalues you have in there. So, and there are other, you see, once you understand that you don't need to get to think strictly about the von Neumann entropy, and you only want to find some quantity that tells you how many non-vanishing eigenvalues the matrix has, then you see that if you look at other powers or other functions of the eigenvalues that for some reason are easier to evaluate, that's fine. You just have to make sure that for the quantity that you are trying to evaluate, there are no caveats in using this measure of entropy. So there's no reason to restrict yourself to thinking about the von Neumann entropy. It's one possible quantity. It's usually very impractical. It is useful because it has some theoretical properties, abstract theoretical properties, but when you actually try to calculate quantities, it is almost never useful. And the practitioners in quantum information, in statistical mechanics and so on, know this for quite some time. Okay, now, since we mentioned quantum field theory, this size of the matrix of size of Hilbert space is it's really a factorial in the average number of particles. This is something that we're used to. So in this case, all these quantities S, P, S, H2 are all proportional to n, so they are extensive. Because the log of n factorial is n in my approximation. Okay, another quantity that we would like to defined is information. Simply it's how much is the entropy, or in this case we can do H2 how is it different from a thermal state? A thermal state, we say, has, or maximally mixed state, has no information. In a pure state has maximal information. And the difference is what we call information. Again, these are physicist definition with physicist precision. All these have a much more precise mathematical concepts, and you can define them with lots of words, but that's what they are. So in this case, we can calculate, right, for if rho is pure, the information is log n, and if rho is maximally mixed, I is 0. Okay? Very good. Any questions so far here about what we have learned? No? Good. So the next concept that I will need is called the thermofield double. So suppose that you have a state, a pure state, that has this form. Again, it's in a bipartite. Sorry. So this is a pure state, right? Because it has a wave function. But it's a pure state with specific coefficients in the sum. And as you can see, we take, this is in an energy basis. So we think we have some Hamiltonian. And we know what the energies of the states are. And in this case, we take the coefficient, the specific coefficient. We take this states with the same energy from space 1 and space 2. And we have here e to the minus beta ei over 2 as coefficients. Okay? This state is called a thermofield double. And the reason is the following. If you look at the density matrix of this state, so it's psi, this is sum I, j, e to the minus beta ei plus ej divided by 2, ei1, ei2, ej1, ej 2, right? And now, if we compute the reduced density matrix of the reduced density matrix rho 1, we need to, right, to do this trace, so we already know how to do it. It's some M2 rho M2. And in this case, you see what happens is that this gives me sum over ij delta im delta jm e to the minus beta ei plus ej divided by 2 ei1 ej1. And so this is sum I e to the minus beta ei. Now the 2 has gone, ei1, ei1, which is, what is this state? A thermal state, right? This is a state whose probability to be in energy E is e to the minus beta E. We see that beta is the temperature of this thermal state. And that's why the original state is called a thermofield double. Because if you now run the calculation backwards, you have a thermal state, and you find the so-called purifier of that state. You find a state, you completed the thermal state with another part that was supposedly missed to get a pure state. And this you can always do. Okay? Again, no problems with unitarity, quantum mechanics, and so on. This is just following the rules of quantum mechanics. Now, this, if we calculate in general S of rho 1, this is called entropy of entanglement. Or sometimes it's just called entanglement. So, and we see in this case that if we have a TFD, then it's maximally entangled. Right? Because the resulting state is maximally mixed, thermal maximally mixed, so its entropy is maximal, and that's why we call it maximally entangled. And if we have a state that is a product state, its entropy of entanglement S vanishes. So in this case, if the state is a product state, its entropy vanishes. Because I take the trace and I get just one of the states. So now we can now we are ready to present problem 1 and problem 2. So let me do it here. Problem 1 and problem 2 will allow you to get to calculate the quantities that we have just met for some simple cases. So problem 1 is so take a density matrix that has size n by n, so it's an n by n matrix, real, and then take k eigenvalues of a size of magnitude x, and then n minus k eigenvalues of magnitude y, and then calculate the quantities that we have encountered, PR, H2, and I. And when you do, it's a very simple calculation, and then consider the cases x much bigger than y much bigger than x, and x similar to y. Okay, so basically eigenvalues of two sizes, a number of eigenvalues of one size, a number of eigenvalues of a different size, and then you will be able to see that the participation ratio, the entropy, the von Neumann entropy, the Ramy entropy, and all of that essentially measure an effective number of non-vanishing eigenvalues. Okay, that's the idea of the problem. Problem 2 is more or less the simplest example of this bipartite system, and then take the singlet the singlet state, right? This in the, I hope that you're familiar with this notation of the spin up and spin down. And then in the one, right, in the 1, 2 basis, you should calculate the density matrix. So how big the density matrix, what is the size of the density matrix in this case? 4 by 4. You were right the first time. Right? You see that it's 4 by 4? Because we have up, down for the first space, up, down for the second space. So we have a 4 by 4 matrix. And the second calculation is to calculate row 1 and row 2. So you have to take the trace over the first spin, then take the trace of the second spin, and then calculate S1, S2, P1, P2, H21, and H22. And then D show that if I calculate an expectation value of an operator that depends only on the spin 1. So an operator in space 1 is essentially a matrix. So we have to calculate, in this case, an expectation value in this state and show that this is equal to trace of rho 1, O1. Okay, are the problems clear? Very good. Okay, so after this quite long digression, we would like to go back to the page model, because remember, our goal was to find ways to evaluate the properties of the reduced density matrix. So now we have the tools, and we can go back and check what the tools tell us about that. Yes, a question?
Quickly, but then when you said phi 1, 2, is phi 1 meant to be maximally mixed then? When S equals 0. So the product state between phi 1 and phi 2, are we saying that phi 1 is thermal and phi 2 is just some other state?
Where? The upstairs or?
Yes, not upstairs, sorry.
No, you will, if you did this is for the thermophile double?
Yeah, so how is phi 1, what is phi 1 and phi 2 then? Psi 1 and psi 2. At the bottom, underneath TFD maximally entangled, you have psi 1. Psi 1, 2 is equal to the product of state psi 1 with psi 2.
No, in that case, so, okay. This, I should draw a line. Okay, let me not do that because there should be a line separating. So the TFD is a maximally entangled, and the other one is the minimally entangled. So it has 0. I didn't separate them. So it's actually a pedagogical mistake, but I hope you forgive me. Okay, so now we would like to go back to the page model. And now we know quite a bit on properties of density matrix, reduced density matrix, and what have you. Right, so you remember this is the setup is still on the board. And we would like to write it as sum of rho A, I, B, J, A, I, B, J, where I and J go from 1 to n, and n is e to the s black hole. So this is the size of the black hole Hilbert space. And A and B go from 1 to m, and m is e to the s rad. It's the size of the radiation Hilbert space, and we think about the case where m, n are much bigger than 1. Okay? So both systems are large, but one of them can be much larger than the other, or the rest, that we don't commit. Now, in this case, we know what rho AI Bj is. It's V AI V star JB, where VAI is essentially the coefficient of this basis element in the wave function, and in this case, some VAI star is equal to 1, it's just a normalization. And rho rad, the reduced density matrix for the radiation, which is the goal of our calculation, is traced over the black hole of rho, which is simply sum over I, VAI, V star, BI. Okay, so we have all the formulas. And now comes this idea. In fact, to evaluate this, we follow a paper from 78 by Lubkin. Is to treat VAI statistically. Now, these VAs are, in this description, random vector of size, of unit size, right? Because of the normalization. So they are random vectors on a sphere. And Lubkin took the simplest probability measure on the sphere to be uniform. So the technical term is uniform probability with respect to the Haar measure. So you can, and then he just calculated trace rho and trace rho square, which is what we need. And he didn't calculate H2, so he calculated the purity, but we can now easily calculate the Ramy entropy. And let me present for you a quick and dirty way to reproduce the Lubkin results. Okay? And of course, so first, when you average over the sphere, you normalize this average to 1. So, right, this is the first Now, the second one is essentially saying that when you do dv, vai, v star, bj, this is some normalization factor, delta AB, delta ij. So essentially telling you that the average of specific eigenvalues square is non-vanishing, and the average of different entries, different matrix elements, is 0, because they are randomly distributed. So you can think about it as a propagator under some path integral. Now, we can use this to find out to normalize the density matrix. So we would like that the trace of rho rad is equal to 1. So we would like this to be equal to 1. So in this case, we see that 1 over this normalization factor, sum A delta AA, sum J delta JJ, should be 1. This is, how did I call it? M times N. So N is M times N. And if I wish, I can normalize the V's like so that the normalization becomes 1. Now, we come to the main results that will allow us to understand Page's result, and that's the calculation of the purity of this radiation density matrix, which Lupkin did. Can I erase the problem? Very good. So now I want to calculate trace rho rad square. So this is equal to, well, let me write it like that because I'm using m and n much bigger than 1, so I'm neglecting the subleading terms. So that's integral dv sum ij a b of VAI V star IB, that's 1 rho rad. Then I have to multiply it again by VBJ V star JA. So the B's here are the same because I'm multiplying a matrix. And the last indices are the same because I'm taking the trace. Okay, so I multiply rho times rho, and I take the trace. So this is equal to 1 over mn square. I didn't tell you yet how to evaluate this. I have to, okay, let me do it like so. So var over mn square. And now I have sum ij ab And I have, like so, I have delta ij, delta ji, delta aa, delta bb, plus delta I, delta jj, delta ab, delta ba. Think about it as contractions between the vectors. So this is equal to 1 over mn square, m square n plus n square m. So it is equal to m plus n divided by mn. Very simple result. Now, if we wanted to calculate the von Neumann entropy, we would be in big trouble because we would need to calculate the log. But since we are calculating now just the purity, it's a much simpler quantity. Let me rewrite this in terms of the size of the M was, right. This is essentially the page result. I will explain how it is related. Okay. So we know the answer, we just don't understand it yet. I'm not sure that we have time to fully understand the answer, but let's try to look at it. So try to look at it for a while and think about how this function, the purity, looks like. Okay? So initially, S black hole, right? S black hole and S rod, you should think about as the e to the S black hole and e to the S rod is the size of the in and out spaces. So initially, everything is a black hole. Then what is the purity in that case?
1.
No. Because I'm tracing over the black hole. So in that case, e to the S black hole is much, so initially, right? So what is the answer in that case?
Exponential minus S, right?
Yes. Well, it starts with it starts with 0, right? And as the radiation proceeds, it becomes a very small number. So we should, because M and N were very large, we cannot really discuss the case. So it's always e to the S rad and e to the S black hole. So in that case, what is H2 of the radiation density matrix? You remember what H2 was? If you don't, you can look up on the board. S rad, right? So in this case, how does the radiation state look like? Thermal, right? So initially the state looks as a thermal radiation. Okay, then what happens when let's say when the black hole has evaporated for a long time, and now S rad is much bigger, so the size of the Hilbert space of the radiation is much bigger than the black hole. What is then the purity? You can do this calculation. E minus S black hole. But this is decreasing, right? Because the black hole is evaporating. So, right, formally when S black hole becomes 0, so when it has completely evaporated, the purity becomes 1. So, in this case, it is telling us that eventually that the radiation is pure at the end. Very simple calculation. Now, there is a better treatment, so for the sake of the people who will not be here later in the next lecture, let me draw the curve of this, and then I will explain in the next lecture how I drew this curve. This is the page curve. So if I draw now, again, I'm not, because I'm at the end of my time and I don't want to go over time, I'm not explaining exactly all the concepts that I have here, but if I'm calculating now the Ramy entropy of the radiation versus n, the number of emitted particles, so the size of the radiation Hilbert space, I get initially a linear curve that goes up, and then this S black hole is essentially is S black hole of 0, the initial size, minus, so the size of the radiation Hilbert space is increasing, the size of the black hole is decreasing, and decreasing in proportion. So in this case, eventually we get H2P becomes 1, and H2 becomes 0, and this crossing point is when e to the S rad is about e to the S black hole, and this is called, so this is S black hole of 0, and this is called the page time. I will explain some of the details here, and this is the celebrated page curve for the entanglement entropy of the outgoing radiation from a black hole using this type of setup. So I will stop here. Thank you very much.
Do you have questions?
Yes.
For a black hole, which are the quantum numbers to describe it?
So here I was actually, here as I discussed, I said there are really no explicit dynamics. So that's question. But the idea is that here you just have a neutral black hole, so a Schwarzschild black hole, and so the only quantum number is the mass.
So you have different masses.
Yes, so the size, as I will explain in the next lecture, is really corresponding to, I can correlate it with time or with the amount of energy that remains in the black hole and the amount of energy that was emitted in the radiation. Because it's evaporating, the mass is varying, and that is what really determines the size of the Hilbert space. But as I said initially, the discussion is really has a quantum information flavor rather than a dynamical flavor. And what I will do when I will discuss the firewall mechanism is I will combine these quantum information ideas with a more dynamical approach, and then we can ask some questions.